Hello, my name is Mackenzie Maxwell, and for my Lab 5, I decided to do the Slinky drop. The purpose of this lab was to measure and model the motion of a stretched Slinky drop from static equilibrium as it falls to the ground and determine if the bottom of the Slinky model stays stationary for a few moments before falling with the rest of the Slinky, just like in the video. For this lab, I used Tracker to determine real-world data values of the Slinky drop from a certain height, producing usable data values for analysis, and I also used Python code to model the Slinky in a perfect scenario. This eliminated all other sources of friction not accounted for in the real-world model. In the end, both the Python data and the Tracker data displayed a strong resemblance. In both models, it was shown that the bottom of the Slinky remained stationary even after the top of the Slinky was dropped from static equilibrium until the Slinky reached its relaxed length. Only then did the bottom of the Slinky begin to fall. There are three key concepts in this lab: Newton's second law, which is the conservation of momentum, which is Vf equals Vi plus F net over m times delta t. And in this lab, we have F net equals F of g plus F of drag plus F of Slinky. There's also gravitational force, which is below, and also drag force in this lab. Here is the tracker model for this lab. I went under the assumption that these men are 6 feet tall, so I made the calibration stick 1.8 meters tall. I then positioned the coordinate plane where the origin is at the bottom of the Slinky, and then used Tracker to point the point mass of where the bottom of the Slinky was at any given moment until the Slinky hit the ground. The initial conditions are to the left, and as you can see the Y position graph, position versus time graph, on the top right here. This is the Python code that I used to make comparisons with my tracker data. The ball, which is the Slinky, was 2.5 kilograms. The position was the initial position on my tracker data, and the initial velocity was 0 in the X, Y, and Z direction, which we only care about the Y direction in this lab. The t equals 0 and the delta t is 0.1. I just chose a small number for that. Gravity is 9.8 and j hat was in the y direction, which is what I initially said just a few moments ago. The drag was 2.6. In this first while loop, I outlined when the bottom of the Slinky was stationary, which happened when time was less than 2.5 seconds. As you can see, you have the momentum principle where I updated the object's velocity and position. You can see that below, and I advanced the clock, and this would prevent a graph. Then once the bottom of the Slinky began to drop, I had another while loop that outlined the entire Slinky moving as one object, the top and the bottom at the same time until it hit the ground. This is a very similar code to the code on the left of the first while loop, and you can see that it also incorporates the momentum principle and the updating the object's velocity and position. It's just in a different manner. In conclusion, both of the models above and the graphs have a strong resemblance. The data from the tracker model has a slightly steeper slope than the Python model, but they overall show the same thing. Because the force of the spring cancels out the force of gravity, which means it would be F net equals 0, the bottom of the Slinky remains motionless for a period of time, and that was in our data around 2.5 seconds. When the Slinky is at relaxed length, meaning the top and the bottom are together, the F net is no longer 0, so the bottom of the Slinky begins to fall with the rest of the Slinky. This means that the force of tension / the force of the Slinky does not overcome the force of gravity, which causes it to fall down. Some potential sources of error are discrepancies in recording. I was unable to perform this experiment with my own Slinky, so I had to find a video online to do so, and by this I had to record with my phone, which is not really a stationary video. So that could have also been a source of error. There could be errors in the tracker software, meaning I didn't use the point mass to correctly outline where the bottom of the Slinky was. There could also be errors using the Python software. And finally, there could be other frictions not accounted for. Thank you for watching.